In this video, we're going to be talking about vibration modes. Um, so we can think about vibration modes from the perspective of a first order system or an uncoupled system that we've discussed before. If we've got mx double dot plus kx equals 0, this is an undamped, uncoupled system, similar to the undamped systems we were talking about in the last video. And there's a special frequency that is going to make this system vibrate uh, at a high magnitude. That's the natural frequency. It's square root k over m. And when you excite this system at its natural frequency, then it does something special. The magnitude of the output shoots way up. You get much more vibration on the output than you put in on the input. And with a um, coupled system, for example, this system that we've been discussing, if you've got some undamped two mass system, so if there's two masses, if there's 2 degrees of freedom, then there are going to be 2 special frequencies that get this system to do something interesting. And those frequencies, we refer to them as modal frequencies. And they they come from the eigenvalues. They're related to or proportional to the eigenvalues of the system, which we refer to with lambda. And at one of those frequencies, both of these masses will oscillate together. So when one mass goes to the left, the other mass goes to the left, and they move together at that particular frequency. And at another one of those, at the second modal frequency, you'll get a different vibration mode, is what it's called, where if one mass is going in the other direction, this mass goes in the exact opposite direction. And those directions are given by the eigenvectors. So with lambda 1, you're going to have some eigenvector u that's equal to a positive number and a positive number. And that means that the direction that the masses moves together. And with lambda 2, this is a 2-mass system. There will be 2 eigenvalues. U2, like this U1, they're vectors. And that's going to be a vector where one of the values is positive and the other one is negative, or they have opposite signs. And that means that those masses are going to be moving in different directions or in exact opposite directions. And so I'm going to put in some videos here. This is for a 3-mass system. So a 3-mass system, go ahead and write down real quick. So we remembered that we're looking at some minus lambda m plus k times u equals 0. And when we solve this, so the lambdas are going to come from, those eigenvalues are going to come from the determinant of minus lambda m plus k equaling 0. And we can find 3 eigenvalues using that. And then we can plug those eigenvalues back into this equation and solve for the eigenvectors. And when we do that with a 3 degree of freedom system, we'll find 3 different eigenvalues and 3 different eigenvectors. And so for this first one, we'll put the video in. With this first eigenvalue, it's the smallest eigenvalue, so you can see these masses are moving at a low frequency, but they're all moving together. The eigenvectors all have some sort of plus, plus, plus. They're all in the same direction. For the second eigenvalue, it's going to be an intermediate frequency. The next smallest eigenvalue. The eigenvectors are going to be plus, 0, and minus. So you can see that when one of those masses on the outside is moving in the positive direction, the one on the far other side is moving in the negative direction, but the mass in the middle doesn't move at all. And at these particular and when this happens, it happens at the particular frequency given by the eigenvalue. This last video, we'll put it in, has a plus, minus, plus eigenvector. And you can see this is the fastest one that we've seen that has the highest frequency. And the first and the last mass are moving together because they both have the same sign in the eigenvector. And the middle mass is moving in an opposite direction from those outside masses. And so this is kind of the benefit. This is how we use eigenvalues and eigenvectors in our analysis of these coupled systems. They allow us to predict the frequencies that we're going to get these modes at, and what directions and what these modes are going to look like. And so we'll go ahead and take a break and stop that video there.